The word oblique means slanted or indirect, which feels about right for these triangles. They don't have a clear right angle, they don't follow the nice Pythagorean rule, and honestly, they make us work harder. It's like the triangle equivalent of someone answering a yes or no question with a poem. Beautiful, but slightly annoying. Think of the law of cosines as Pythagoras for unruly triangles. Right triangles are well behaved, they follow clean rules. But oblique triangles? They're chaotic. No 90 degrees angle, just attitude. That's where cosine steps in, acting like a correction officer. It says, fine, I'll still find the missing side or angle, but I'm adding a cosine term to keep things in check. And if the triangle does happen to have a right angle, cosine politely vanishes, and the formula turns back into classic Pythagoras, like nothing ever happened. The law of sines says, in any triangle, the sides and their opposite angles should stay in proportion. It's beautiful symmetry. The bigger the angle, the longer the side facing it. It's great for finding missing sides. Reliable, elegant, and peaceful. But when it comes to finding missing angles, you need to proceed with caution. Why? Because sine doesn't care if your angle is acute or obtuse. It gives the same value for supplementary angles. Like sine of 30 is 0.5. Sine of 150 is also 0.5. That's how you end up in the dreaded, ambiguous case, where the triangle could have one solution, two solutions, or none at all. So yes, the law of sines is wise and poetic, but also a little mysterious. Always check the situation before trusting it completely. If I ever decide to trick you in a test, I would give you 3 lengths that cannot form a triangle. It sounds innocent. 3 sides, what could go wrong? But not every trio of numbers makes a triangle. The triangle inequality says, the sum of any 2 sides must be greater than the third. That's not just geometry, that's common sense. If 2 sticks taped together are shorter than the third, they'll never meet to form a vertex. You don't get a triangle. You get, well, I don't know, a wish to be a triangle. So always test your triangle first. If it fails the test, you're not solving a triangle. You're chasing a geometric illusion. In the SSS case, you know all 3 sides of the triangle. Now it's time to uncover the angles. The law of cosines is your first move, especially to find the largest angle opposite the longest side. Why start there? Because cosine doesn't get confused. It knows the difference between acute and obtuse. Here the largest angle turned out to be acute. That means the other 2 will be acute as well. In the second step, we used the laws of cosines again. We could use the law of sines to get the same answer. But cosine did all the heavy lifting, so that sine could chill. Note that if you prefer not to use the law of sines in the SSS case, then the order in which you find the angles doesn't really matter. Because, like I said earlier, cosine doesn't get confused. It knows the difference between acute and obtuse. Cosine is like a reliable accountant who always balances the accounts perfectly. Here we have an obtuse triangle, but you can't tell just by looking at the sides. The triangle doesn't come with warning labels. The safest move is to calculate the largest angle first using the law of cosines. If you start with one of the smaller angles instead and then use the law of sines to find the largest, you will get its acute evil twin. Then you use angle sum to get the third one and get something over 180, which is geometrically impossible and mathematically embarrassing. Here's the SAS case. That's two sides and the angle in between. No room for guessing, no ambiguous nonsense. This triangle tells you what it wants, and it wants the law of cosines. You start by finding the missing side. Once you have all three sides, the triangle settles down and becomes a classic SSS case. From there, you can use the law of cosines or law of sines to find the other angles. But remember, cosine is your safest bet for the big ones. In step 2, I used the law of sines to find angle B. This is safe because angle B is the smallest angle and definitely acute. So when a triangle shows up all sassy, don't panic. Just hand it to cosine. It knows how to handle the attitude. Using the law of sines to figure out side lengths is as safe as using a ruler in math class. It just works. These triangles are calm, cooperative, and completely determined. Once you know two angles, the third is easy. Just subtract from 180. After that, you use the law of sines to find the missing sides. No ambiguity, no twin angles hiding in the shadows. It's like the triangle already did half the work and just wants you to finish it off. So if you see AAS or ASA, take a deep breath. You're in friendly territory. It's the trigonometric equivalent of a group project where everyone actually did their part. It's very easy to remember which case is ambiguous, because it's SSA. And yes, when you flip it, it spells ASS. That's not just a coincidence. This case is the troublemaker of triangle land. You're given two sides and an angle that's not between them, and the law of sines seems eager to help. But here's the catch. It might lead you to one triangle, two triangles, or none at all. It depends on how long the sides are and how the sine values behave. So be careful. Always check the possibilities before moving on. SSA doesn't guarantee a solution. It invites a mystery. Sir Isaac Factorton once said, "Never trust a triangle that hides its angles. Use the right law, reveal the truth." He was talking about SSA. This is the triangle that never was. You're given two sides and an angle, plug it into the law of sines, and suddenly, the sine of an angle turns out to be greater than 1. That's your cue. Hit the brakes. This is not a triangle. It's a mathematical fantasy. Remember, sine values can never be more than 1. Thus, no solution in this case. Welcome to the mysterious quantum trigonometry. This is the case that gives you multiple possibilities. You plug values into the law of sines, and surprise! The sine of an angle turns out to be valid, but not unique. That's because sine doesn't know the difference between an acute angle and its obtuse supplementary twin. So you get two possible angles, which means two possible triangles. The first one you get is acute and the second one obtuse. Both are valid, and both meet the original criteria. The Schrödinger's triangle of trigonometry. It is both alive and dead, until you collapse the wave of possibilities through your consciousness. These triangles go to their AAA support group every week to talk about their deep-rooted fear of committing to a scale. It's not Alcoholics Anonymous, it's All Angles Anonymous. They've got their identities figured out, but ask them for a side length, and they freeze. It's not that they're hiding something, it's just that they could be any size. Infinite triangles, same attitude. They are transparent about angles, but they'll never give you concrete measurements. Remember how we used to find area using base times height over 2. That works great if you have a height. But oblique triangles rarely cooperate like that. They lean, they slouch, they don't give you right angles. So instead, we use what we do know, 2 sides and the angle between them. It works like a charm. Turns out you don't need height to find area. Just 2 sides and a little bit of trigonometric faith. It is said that while solving a triangle during his apprentice days, young Isaac Factorton made a critical mistake. He rounded too early and ended up with an angle sum of 179.8 degrees. From that moment on, he swore a sacred oath. Never again would he round in the middle of a solution. Instead, he stored intermediate results in his mystical Sharp EL 531 calculator and only rounded when the final answer was at hand. Let his wisdom guide you. In trigonometry, every decimal digit matters. Round early, and risk mathematical shame.